Hey everyone, welcome back. So you have successfully completed part 1, where we laid the groundwork with the introduction to carbon and covalent bonding. Now let's move right into Class 10 Science, Chapter 4, specifically Part 2, the versatile nature of carbon and the homologous series. We already learned the basics, but today things get truly fascinating. We're uncovering the ultimate secret of carbon, scaling up from single atoms to the very building blocks of our entire world.
Let's just jump right into a massive chemical mystery. Have you ever actually wondered why carbon forms literally millions of compounds, while most other elements on the periodic table struggle to form even a handful? I mean, what exactly makes carbon the absolute VIP of the periodic table? Here is our roadmap for this explainer. First, the carbon mystery. Then, secrets of versatility, bonds and chains, families and functional groups, and finally, carbon in daily life. Okay, Section 1. The carbon mystery, building the world. Think about it. From the petrol and diesel in our cars to your cooking LPG, the sugar in our food, everyday plastics, life-saving medicines, and even the proteins inside your own body. They are all carbon compounds. It's an ever-expanding universe of chemistry, and scientists are discovering new ones every single day. It's kind of mind-blowing, right? Moving right along to Section 2, Secrets of Versatility, Nature's Ultimate Lego Brick. So, the word versatile literally means able to do many different things. And carbon? Well, carbon is the ultimate chemical shapeshifter. Its extreme versatility, its ability to just play well with almost anything and form a massive number of compounds really comes down to two fundamental microscopic rules. Rule number 1 is tetravalency. Think of a single carbon atom as a central hub with exactly 4 connection pegs. Because it has exactly 4 valence electrons, it forms exactly 4 covalent bonds. This clever setup allows it to seamlessly snap together with a whole bunch of elements: hydrogen, oxygen, nitrogen, sulfur, chlorine, and crucially, other carbon atoms. And that brings us perfectly to the second rule, catenation. This is basically carbon's unique superpower to infinitely link up with identical carbon blocks. It doesn't just bond with other elements, it absolutely loves bonding with itself, creating a vast, almost limitless foundation for structures. Because of this catenation superpower, carbon chains don't just go in a boring straight line. They can branch out in complex directions with side branches attached, or even loop entirely back on themselves to form closed ring structures, like benzene. It truly is nature's ultimate Lego brick. Let's dive into Section 3, bonds and chains, saturated versus unsaturated. The absolute crucial distinction here is between saturated compounds and unsaturated ones. Saturated compounds, like ethane, use only stable single bonds. They're called saturated because carbon's bonding capacity is completely filled up, making them structurally chill and less reactive. On the flip side, unsaturated compounds like ethene or ethine use highly reactive double or triple bonds. Their capacity isn't maxed out, making them much more reactive and ready to mingle chemically. Now, when carbon snaps together exclusively with hydrogen, we get what are called hydrocarbons. These are incredibly important fuels that literally power our modern world. Think about methane, ethane, propane. These are pure hydrocarbons, containing absolutely nothing but carbon and hydrogen atoms perfectly bonded together. Moving to Section 4, families and functional groups, organizing the chaos. So, with millions of variations out there, how do chemists actually make sense of the chaos? They organize them into families called a homologous series. And just a heads up, this is a frequently asked board question. To be in one of these families, the compounds must share the same functional group, exhibit similar chemical properties, show a gradual shift in physical properties like boiling and melting points, and successive members have to differ by exactly 1 CH2 unit. It's a brilliantly ordered system. Just look at this pattern in the methane family. Notice how each successive member simply adds exactly 1 carbon and 2 hydrogens. Methane starts us off at CH4. Snap on a CH2 block, and you get ethane at C2H6. Add another, you get propane at C38, and then butane at C410. It's a perfectly predictable, steady ladder. But what if you want to change a compound's behavior entirely? That is where you add a functional group. Think of a functional group as a specialized software update for the molecule. It's an atom or a group of atoms that completely overrides the base structure and dictates exactly how the compound will behave chemically, no matter how long the main carbon chain happens to be. Here are the heavy hitters you definitely need to know. Alcohols, represented by an OH group, like an ethanol. Aldehydes, represented by CHO. Carboxylic acids, which gives us everyday ethanoic acid, better known as vinegar, through the COOH group. And ketones, with a carbon double bonded to an oxygen. Attach just one of these groups, and you completely transform the compound's entire identity.
Because of this extreme organization, naming these compounds systematically is actually a breeze. It's based purely on the number of carbon atoms. 1 carbon is methane, 2 is ethane, 3 is propane, 4 is butane. Once you learn the rule of counting the carbons, you can systematically name practically anything.
And finally, Section 5, Carbon in Daily Life, the ultimate payoff. Because of tetravalency, catenation, and functional groups, carbon really is the essential ingredient in almost everything you interact with. Petrol, LPG, the cooking gas in your kitchen, plastics, medicines, your cosmetics, your food, the very fabrics you wear. Modern life would literally be impossible without it. The whole shebang rests squarely on the incredible flexibility of the carbon atom.
So, to quickly recap this explainer, we traced carbon's journey from a microscopic 4-peg versatile building block down to its tetravalency and catenation rules. We looked at straight, branched, and ring chains, and decoded saturated versus unsaturated hydrocarbons. Finally, we explored the homologous series and how functional groups and systematic nomenclature act as the rules governing millions of compounds.
We've seen how carbon basically builds our current world. But here's a thought for you to ponder before we go. With millions of carbon compounds already discovered and practically infinite ways to snap these elemental Lego bricks together, what world-changing material is sitting out there just waiting for us to discover it next? Why exactly is carbon called a versatile element? Drop your answer in the comments below and keep exploring the amazing chemistry of our universe.